Welcome. Good morning, afternoon, and evening, everybody. We've got a great crowd. I'm loving where everybody is from. We are officially global. I love to see it. We're going to go ahead and get started. This is a historic webinar that High Sky is hosting. We're honored to welcome Joby Aviation here. Please keep your cameras off and stay muted until we get to the Q&A session at the end. Also, happy Martin Luther King Jr. Day, everybody. Also, happy Inauguration Day or unhappy Inauguration Day, depending on where you lie. But it is an interesting time in history for sure. So thank you for joining us. There's a lot happening. It's a holiday. Everybody's on TV. So thank you for spending your time with us today. We are very grateful. I'm Danielle McLean. For those of you that don't know me, I'm the founder and CEO of High Sky Society. I started this company in 2023. We are officially 2 years old this month. So happy second birthday to us. And I'll tell you a little bit about High Sky. So we'll go through some announcements and then I'll bring on our distinguished speaker. So High Sky Society is a 501c3 nonprofit committed to decarbonizing aviation and aerospace with hydrogen. We welcome innovators from eVTOLs, advanced air mobility, fixed-wing aircraft, and spacecraft. Our mission is simple. If it defies gravity and uses hydrogen as fuel, it's part of our vision for sustainable flight. So yeah, our objectives include workforce development. We equip future professionals with hydrogen skills, community engagement. We build positive community relationships, education. We provide industry-leading courses and webinars, advocacy and awareness. We advocate for your hydrogen solutions. Our monthly sponsors are SoCal Gas, Hayaseki Aircraft, Vertical Flight Society, and Thurman Co. We would love for you to become one of our next sponsors for High Sky Monthly. We're getting ready to announce a membership program that includes sponsoring of these webinars. And they are live here. As you see, loads of guests attend. And they also go on our YouTube channel where they live forever. So if you sponsor or become a member, your logo lives forever on our YouTube channel. So what is High Sky Monthly? High Sky Monthly is a series of free educational webinars with new distinguished speakers on the third Monday of each month. This is our hint webinar, if you can believe it. All of these webinars are on YouTube. High Sky has the largest collection of hundreds of hours of expert hydrogen aviation videos, the largest collection in the world. And if you're interested in subscribing to our YouTube, we would sure appreciate it. I'm going to stick the link in the chat. You can push that to subscribe. I don't think you'll find anything else like it on the planet. So High Sky Monthly is what you're on now. High Sky Pod is High Sky's podcast, which is also on our YouTube channel. Some notable guests that we've had on on the High Sky Pod is Dr. Martine Rothblatt, the founder of SiriusXM, and she's also working on hydrogen eVTOLs. You can watch that interview with Martine and me. I'll put that link in the chat. Another notable interview is Dean Kamen, the inventor of the Segway, who's also working on electric choppers. That was a really fun interview as well. I'll stick that link in the chat for you also. So subscribe to our YouTube. That's the short version. We have a lot of cool content and we're growing. So as I mentioned, we have an educational arm, and we just recently released our Advanced Hydrogen Aerospace Technologies and Design online short course. You can take the course anytime and watch the videos at your convenience. This is a must-have for anyone interested in liquid hydrogen storage, designing hydrogen-powered fixed-wing and or eVTOL aircraft, and advancing hydrogen at airports. This is a 20-hour course with 10 lectures. We did this in partnership with AI, and you can register for the course at any time. Right here, I'm going to put the link in the chat. Can you all see and hear me okay? Now that I'm back, please put a 1 in the chat if you can see and hear me. Awesome. Thank you. Okay, so 2024, we did our end of the year kind of party giveaway. And so our jacket winners are Gail Labris, Sarah Mitron, Edward Gluckler, Norbert Palestine, Steve Ross, and David Eisen. So you all will be receiving your jackets very soon. The weather in Houston this week. Hopefully we'll get those sent out to you this week. So be looking for those in your mail. And then we also had the High Sky 2024 Stars award winners. Person of the Year was Jennifer McAlagwin. Board Member of the Year, Matt Gregory of SoCal Gas. Podcast Guest of the Year, Dean Kamen. And Donor of the Year was Livevolt. So thank you all very much for your contributions to High Sky in 2024. We wouldn't be where we are right now without you. Okay, so as was promised last month and last year, if you attended last month, you were promised to be in a drawing to win tickets to Flying High of 2025. So I'm going to push this button and I guess I got to click to spin. I don't know if you have to be present to win. This is fun. I've never done this before. Hey, Sant twins. Santia of Leptcar. That's awesome. I don't know if he's here. I'm just gonna do another one just in case he does have to be present. I don't know if he's here or not, but I'm just gonna do 3. Ron Epperson. Now I don't know if you'll win because it's gonna depend on whether or not the others. I don't know the rules. Rishab set the rules. This will be the last one. Dave Frankel. Okay, great. Well, that's fun. Rashad built that, I guess. That was really cool. So Santa's our top winner. I just got to look at the rules. Okay, now is one of my favorite parts of the webinar. I'm going to stop sharing and everybody please turn on your camera, but not your mic. And we're going to take some group pictures. We're getting good at this. It used to take a long time for me to get people to turn their pictures on. All right. Say cheese. Awesome. We're going to do another one. A bit. I'm not as fast as Rishab on this. Say cheese. Gotta do a couple more. Got a big group. Say cheese, everybody. The third group, not many of you have your cameras on. We're still going to try to get you. Okay, I see you coming on. Say cheese. Awesome. One more, I think. Yep, this is the last one. All right, say cheese.
Cheese.
Right, that's one for the record books for sure. You will all be tagged in LinkedIn if you have a LinkedIn profile on that. All right. Awesome. Okay, now for our special guest, let's meet today's speaker, Raffaele Russo. Raffaele Nicholas Russo is business manager, new technologies at Joby Aviation, where he crafts strategic roadmaps for new hydrogen aircraft. He was project lead for the first VTOL liquid hydrogen aircraft, flew 560 miles in summer 2024. Raffaele Nicholas joined Joby Aviation in 2018 as engineering lead for the thermal engineering team. Previously, Raffaele worked at Up Partners, shout out Up Partners and Ben Marcus, Tesla, and Ferrari Formula One. He received his aerospace BA and mechanical engineering from the master's in engineering from the University of Cambridge. Sorry, mechanical engineering. I guess that's what that means. Please correct me if I'm wrong. And his MBA from Harvard Business School. Without further ado, please welcome today's speaker, Raffaele Russo. And just one quick note, put your questions in the chat as he goes through his presentations. And then at the end of his presentation, we'll allow you to come on and ask the questions, but no interruptions during the presentation, please. It kind of derails it. So save them for the end. Okay, Raffaele, the stage is all yours.
Hello, everyone. Great to have you. I'm going to start screen sharing my deck and get right into it. First off, thank you all so much for joining. Thank you, Danielle. Thank you to the High Sky team for this opportunity to speak. I'm very excited about the stuff I will talk to you about. We have a lot to cover. It will center on what you see in front of you, the achievement of flying 561 miles. We actually exceeded this distance after our first press releases. But before I get into it, thank you all for joining on a day that is off for many of you. Thank you for joining from, I've seen at least 4 different continents. I really appreciate you guys taking this out of your time, whether it's time out of inauguration things, out of MLK family. I know that Joby has a great pull, and hopefully I can live up to the standard that Joby's put out in the last 15 years. But I nonetheless appreciate so much that you guys, are here listening to me. And yeah, let's get into it. First and foremost, I will cover a few things. I've put them deliberately in question marks so that we kind of have a focus question and answer that I target. So obviously, this is High Sky. It kind of gives away that it's hydrogen and sky aviation. I will give you my take of why it makes sense specifically to the hydrogen in aviation. So treat it as an extra data point, treat it as the opinion of someone who's done this and has had some experience with the challenges and the benefits. That's somewhat agnostic of Joby specific. It's more, why does this make sense for everyone, for the whole of mankind? Number two, why should Joby do it? I've been at Joby, and I'll get to it in a second, since 2018. We've started this in earnest in 2021. Part of my role is to understand why this is a corporate strategy value. This has corporate strategy value, so why should Joby be doing it versus focusing on other things? And then that third bullet point of how, that's the prototype we flew last summer and have been flying. And lastly, the what's next is more of the roadmap that we see for a valuable product that will actually, answer uh, the worldwide demand. So going beyond the prototype. Of course, this what's next is a corporate strategy, a product strategy of what's the value for people. I will sound a bit more MBA-ish there and less engineering, but it is something, of course, that we've, since before even the prototype itself, we were trying to figure out obviously what's next and thinking a few steps ahead. And then at 9:30 Pacific, 11:30 Eastern, we'll have Q&A and yeah, I'm sure I'll get a bunch of stuff from you guys and questions and remarks. So Danielle already started this, but I'll just double click a second. I do a range of things for Joby since coming back from my MBA. The title is business manager. That doesn't really mean too much per se, but new technologies is 99.9% hydrogen. I do a bit of the sustainability work that this company that Joby really cares about, and the rest of it is hydrogen. Program and project means actually showing up boots on the ground and making things happen, making sure coordination is in place. All the engineers have a sense of the reporting system. Joby has built a hydrogen development team, but it is spread across different continents. I'll get to that in a second, different departments with different execs. And so my role is also to make sure I can zip across those departments, those functions, and make sure that people know what they're doing, collaborate effectively, are understanding the latest, are safe, and a bunch of things more. A third item I'll get to in a sec, towards the end of the presentation, is something I had to manage more in depth, which is a temporary liquid hydrogen facility where we did store, refuel, maintain. We still do maintain our aircraft. And that was a huge effort, and the value will come in a second, but that was one of the core things I worked on. And lastly, I came back from my MBA. I came back to Joby in 21 after leaving my role as engineering manager. I came back after the MBA because Joe Ben, our founder and CEO, and me reporting to him and working closely with him. Joe Ben couldn't make this call. He's very tied up, but is actually a huge fan of High Sky, has attended in the past. He's a tremendous leader and he actually believes so much in hydrogen. He relies on myself, a bunch of people, to really push forward his dream of hydrogen as the next step in the future of Joby. Very quickly, Danielle already mentioned my background. The only things I will add is yes, Engine's Masters of Engineering in Aerospace. I actually have a pretty nerdy background when it comes to everything up to around when I transitioned to business work, doing computational fluid dynamics, doing aerodynamics of wind tunnels, 3D printing components, and putting paraffin oil. So that element of aerodynamics and thermodynamics, which is actually a key part of the pros and cons of hydrogen, is something that I've been studying since undergrad, honestly. So it is one of the biggest nuances of hydrogen, the thermodynamic element of it, and of course, for all of aviation, the aerodynamic part of it. But it is something that initially got me excited into the space and made me appreciate the value. The other thing that's valuable of this slide is the fact that I spent a while in electric. So it's not like I showed up and in the workforce as a firm believer of hydrogen from the beginning. This is the only answer. Electric sucks. But rather, I spent significant time at Ferrari, the Ferrari cars, the F1 cars on the team I was in. Believe it or not, they're hybrid. They have a battery, and they actually use that in boost. So from Ferrari F1 to Tesla, and then Joby. Initially, Joby was electric only, right? Joby is still electric only, but the team was focused on exclusively the electric product. So I have had plenty of time to appreciate the huge value that electric cars, electric aircraft bring and will bring to society. And that's, I think, a better platform than coming in blind to electric and going straight to believing aviation must be hydrogen only. Okay, enough about me. Why hydrogen? Of course, you've seen, this is Hi Sky. Many of you come from the space of either hydrogen or aviation. I'm sure you've seen a slide titled Why Hydrogen a million times. I will try and make this as um, specific and tailored to what Joby believes, what I believe, what someone who's done the work believes. So in some sense, I don't just say this, I actually see it, having done a bunch of research and development on the space. But it really started in the public eye only last year. Joby tends to be quiet about things until they're happening or have happened. In other words, we didn't really tell anyone, and except for one item, the acquisition of a subsidiary that does hydrogen, Joby didn't say anything until we actually flew 523 miles. And these two snippets are articles that the one on the left I co-wrote with Joe Ben, and the one on the right is the actual fact. So left is the promise, what we think, why we're doing this, and on the right is, hey, we've done something that we think is a huge step. Now, why hydrogen means a bunch of things. Let's start with the biggest one, which is, of course, it's fuel efficiency, it's a weight efficiency. So you've seen forms of these slides in the past. I think what's valuable about this is comparing and combining the value of hydrogen compared to battery and compared to jet fuel, not just on the specific energy basis, but also the efficiency basis. So looking on the right, batteries are tremendously valuable for short ranges, and Joby still is pushing at full steam on the electric VTOL, the eVTOL product for urban mobility. However, everyone's realized and noticed that a trend of battery energy density is improving, but improving at a fixed rate. It's 6% year on year. There's no, promising reason to believe that that will, jump and have an inflection point. So for the sake of longer ranges, we are hitting a product that struggles. In other words, if you try and get from 100 to 200 to 300, these will eventually require so much battery aircraft requires so much battery that you are barely growing your payload for gigantic aircraft. Even with the efficiency of 90%, which is significantly higher than jet fuel and even hydrogen, this remains something that is very hard to scale beyond urban mobility. Jet fuel, is actually a third of the energy density of hydrogen, but what matters here is that the efficiency is about half. So when on the right you see the 6x improvement in net specific energy, what we're talking about there is the fact that hydrogen not only is 3 times more dense per unit energy, the actual amount that makes it um, to your motor, to your actual shaft power, is 6x overall. And to put this in numbers that are more palatable or more directly applicable to something you may be more familiar with that isn't Joby, I'm going to jump back to this in a second. Here's a comparison of the A350 and the A320neo. So roughly, most of its configurations are twice the range and twice the payload of a 350. Of a 320 is the 350. The consequence of doubling the range and the payload from one aircraft to the other is actually a 4x increase in weight, roughly a 4x increase in upfront capital cost. And then that mission burns 6x more fuel. If you normalize that by a per passenger, we like to work a lot in a per passenger per mile. That means that it's still 2x heavier, 2x the capital cost, and 3x the fuel. What's very valuable here is the fact that we said it for batteries, you have a lot more batteries as you fly further. That's also a true statement for fuel. It's less appreciable. It's something that today we accept as the status quo, but hydrogen looks to improve this further than what jet fuel can, and basically get to a point where the vast majority of the aircraft isn't carrying everything else, it's carrying people. So at the bottom, we have a future hydrogen airline or a generic. You can fly further, only have 80%, but decrease 5x or have 80% less energy per passenger per kilometer. The other tremendous part, which I'll get to in the next slide, is the fact that we believe the reduction in global warming potential is up to 99% compared to a typical jet fuel powered aircraft. You've seen this slide a million times. I will say, Joby believes this. Joe Ben believes this. This is front and center. What we're saying here is that we have many countries in the world have committed to a net zero by 2050. Aviation today is only 2%. You can argue a lot of the things that today contribute a lot of things today contribute a lot more. Wildfires are a much bigger proportion. Maritime transportation are a much bigger proportion. Electricity grid is a high proportion of all those. However, it's one of the hardest to abate sectors. So we don't have clean answers today on how to get that number, that total number, meaning CO2 emissions in tons per year, not percentage. We don't have a good answer to get that lower. So a lot of numbers, a lot of studies I've read through, I've researched, all suggested that 2% of aviation today is likely to increase to 10%. Partly because everything else is going to drop as they try and push to net zero. Partly because luckily larger shares of society are going to have access to travel, and therefore the actual total number of tons per year of CO2 is going to go up. But if we can forecast pretty reliably that 2050, while everything else is going to net zero, aviation is going to higher and higher proportions, higher and higher percentage of the total, we appreciate we need to start moving now. And that's kind of part of the reason, alongside the efficiency argument I just made as to why, it's now, it's 2025, it's 25 years, it's not that far. We don't want to be, the slowest person running from the bear, or the worst student in the room. Aviation shouldn't be, aviation's about innovation. It's about literally putting people in the air, in the sky. It shouldn't be the hardest to innovate sector. It should be ahead of the curve, and be a leader in the path to net zero. An additional point on the emissions is the contrails part. And this is something that has a lot of research backing. There's also research against it. Luckily, a few companies and a few research centers are trying to answer this question more in detail. Contrails are the clouds that form behind aircraft. They have, depending on conditions, altitude, humidity, they have a tendency to dissolve immediately or remain and basically form clouds that ultimately have the same effect as CO2. In the sustainability world, it's typical to talk about CO2 equivalent. What that means is not just the CO2 you're putting out, but actually what's causing global warming. Contrails do not have CO2. They have NOx, they have soot, they have water vapor, they have particles of all sorts, but they're not CO2, and yet they contribute to CO2 like effects, which is why if you actually account just for CO2, you only capture a third of aviation's total climate impact. All the studies converge. There's some studies showing 30%, some studies showing 70%, or between half at 1.5x to 3x. But around most of the research agrees that of the CO2 emissions you see, a double, so 2x for a total of two-thirds, is what you don't see, is what contrails are contributing to by just forming. I'm going to leave this there because it's not itself something that, how does it tie in? How does it change with hydrogen? What matters here is that you need to solve not just the CO2 emissions itself, you need to solve this contrails emission equally or more importantly. A few last things that are worth mentioning, up front are actually, no, this slide first is probably valuable. So this is a comparison that is worth touching upon on why hydrogen electric, so hybrid electric, generally a fuel cell converting hydrogen into electricity, and then from there turning a motor and a prop. How that does that compare to combustion, to traditional jet engines using SAF, and hybrid electric, so battery and combustion combined? What's tremendously important on the left column, of course, we can talk about hydrogen being low in direct CO2. Even combustion only generates water vapor, so there's no CO2 generated from that process. Whereas SAF and hybrid electric, so a gas turbine running, charging a battery effectively, those have emissions. The difference is that non-CO2 part, the contrails. The hotter emissions of an H2 combustion are more likely and harder to abate, and therefore are more likely to produce a contrail. And that's why this circle is significantly more red than the higher one. An H2 electric solution has lower emissions. I'll show you some pictures of the aircraft, of Joby's aircraft, with a little contrail in the back that is actually low temperatures and doesn't form contrails, whereas the H2 combustion or is less likely to form contrails, hence the small little pizza slice. Compared to H2 combustion, it's significantly lower. The technology scalability, a lot of push is going into SAF. SAF is a valuable stepping stone, I believe, and it's a shared opinion among many that it's not the final solution, partly because of the tremendous amount of energy that is required for SAF and it being harder to scale than H2 electric and H2 combustion. So overall, you see on the right, as expected, H2 electric comes up on top. But we do believe that, for the reasons I mentioned all on the left, the net impact in terms of benefit times realisticness, right? The CO2 and non-CO2 impacts times that scalability. That's why H2 electric is the answer. It does provide a lot of benefits that the other ones don't have, and therefore, on top of the earlier argument about range and energy density, and it's argument like these that convinced Joby initially, and then the rest of the company to start venturing into this space well before 2021. What's tremendously important is the fact that the thermal efficiency is higher. We touched on that, but the fact that the thermal efficiency is higher is also due to lower temperatures, and therefore a longer life expectancy, lower temperatures and lower vibrations, lower stresses. What does that mean? When you run a system, and this is somewhat proven with electric cars versus combustion. The only reason you don't see it is because combustion cars have been developed and constantly being developed over the last 100 years, are relatively new. When you're running something at lower stresses, lower vibe profiles, lower temperatures, you increase the life expectancy. In other words, you don't have to replace your part every 5,000 flight hours or sometimes 100 flight hours for some helicopters. You can increase those numbers to higher and higher. Flight hour cost, direct operating cost drops down. Similarly, and equally importantly, that same consequence is that, those unexpected failures, so not life expectancy, but, sudden failures, decrease significantly. Joby's number one value is safety. Both the electric and the hydrogen aircraft, of course, put that front and center. But there's a physics benefit in running low temperatures, low stresses, low vibes to this, which is that you are just decreasing your failure rates. The last two are actually related to a key part of Joby's architecture, which is the six prop. By having, first of all, except for the compressor, fuel cells quiet, so less noise for passengers and surroundings, but also having six props compared to a larger single prop for a given thrust is actually significantly lower noise. Thrust goes with the third power of blade size, but noise goes with the fifth power. So if you can make more smaller props, you're actually benefiting from a decreased noise. And then the fact that we have significant, and I'll show you more in the later slides about why this is true, but it's easier to build redundancy with multiple motors and effectors. Electric motors are actually easier to scale down in size compared to combustion. So it's not that much more work to have six smaller props than one large prop, as long as you're flying electric. If instead you're flying with a combustion engine, you either have very complex axles and transmissions, or you leave a lot on the table in terms of weight because you are creating six or multiple separate combustion motors and effectors. Okay, so why should Joby do this? And this is, by the way, a picture of two of our prototype electric aircraft. Joby's been around since 2009, building increasingly more mature versions of its eVTOL aircraft. Why does it make sense for Joby to jump into this hydrogen space? Why now? Why do I have a job at Joby doing this? This is kind of what I want to talk about next. First and foremost, what does Joby do? What is Joby going to launch as its first product? You're in Manhattan, you're trying to get to the airport, you call an Uber, and that Uber takes you to the closest vertiport. Here, an eVTOL, like the one show, takes you to the airport and you're already at a gate. Now, this example is with an airport, and it's showing our partner Uber and our partner Delta. What really matters here is the fact that today, and I've done it many times, JFK to Manhattan is either an hour and a half by subway, or probably even more on rush hour than an hour and a half, and $100+ in a taxi. The multimodal element of this will come back later with hydrogen, but the key thing is that Joby has already started, and by acquiring Uber Elevate a few years ago, has been implementing multimodal ride sharing. All that means is we're looking at door to door. We're looking at how from where you start to where you want to be, we're minimizing that time. So you need various different things. You need a car, you need a VTOL, you need a commercial aircraft. All those options are integrated into what will be our product, launching in Dubai first and in US markets right after. This is significantly different from the model today of aviation travel, of really most types of travel where this multimodal element doesn't exist. So this is the product. What does the aircraft actually look like? This is our eVTOL aircraft. On the bottom left, 100 miles is actually remarkable. And it's an industry leader for range. One key reason it achieves this is if you look, the props are oriented vertically. That means when it takes off, it can take off, without a runway. It takes off as a VTOL, vertical takeoff. You'll notice these props are actually hinged. So once you're in the air, the aircraft actually transitions to flying on the wing, it's called. So flying on the wing compared to remaining in this mode, which is basically the mode most drones fly in, is why you can get to these longer ranges. Flying on the wing is significantly more efficient in terms of lift to drag, in terms of distance traveled per unit energy than flying purely as a prop. Other competitors are flying purely as a multi-rotor or quadcopter, different names for it. But if you remain in this vertical flight type of asset, you dramatically reduce your range. If you manage to transition to forward flight like Joby does, then you are getting in the hundreds of mile range. You're not going to exceed this because, spoiler alert, hydrogen, as we mentioned before, electric is a lot less energy dense than it needs to be to go for the 500 plus miles. But to get to the distances of large urban centers like New York, like LA, 100 miles is actually your perfect sweet spot. In terms of speed, ultimately the goal is to save hours and minutes of travel, so it is significantly faster than ground travel. Additionally, and this is an interesting number, about the average round trip is about 40% more circuitous, a longer route than it is to fly to straight line, like the eagles flies or whatever the expression is. In other words, not only you're saving speed, but you're saving time by increasing the speed. You're also saving time by reducing the distance. If you can fly generally in a straight line, avoiding whichever areas of your urban center you have to. Target payload is 5 people, a pilot and 4 passengers. And then, as I mentioned before, and I'll talk to in a bit more detail, this aircraft is significantly quieter than a helicopter, significantly quieter than a small aircraft and a large aircraft, of course. Joby's doubled down on this. It invited NASA on site to do a bunch of studies on the noise profile of a bunch of aircraft. We have our own Cirrus SR. We got a few other aircraft and helis on board, and then we got Joby. As I mentioned earlier, having forward flight, having multiple props, and having forward flight actually decrease the noise by increasing efficiency, decreasing tip speed. And 45 decibel is actually really, really quiet. You may find on YouTube various videos of Jobin talking while the aircraft takes off behind him. And there's no weird, sound production happening there. There's no targeted microphones. It is really that the aircraft is significantly quieter than anything with comparable capabilities can do today. This element of safety of sound is something that Joby, well before I joined, identified as one of the most important elements for the successful outcome of this product, meaning people actually wanting them. If this is too loud, and a good example is if you've ever been to Rio, you will hear, or really even, South Manhattan, there's a lot of helicopters, a lot of noise. The average population, the vast majority of the population doesn't fly in helicopters, so it comes just as a nuisance. Joby's actively looking to avoid that. If it can be a product that doesn't disturb those traveling and don't travel, it will be extremely more likely to be welcomed by society as a whole because it's a net benefit. It's not a benefit at the cost of waking up in the morning to these. The element of importance of customer acceptance, of societal acceptance, is something that has mattered for Joby Electric. I will touch upon it at the end, but we're taking the same approach for hydrogen. Hydrogen has significantly more reservations from everyone, from the stakeholders that matter in society, and therefore we have to put the element of customer acceptance, of societal acceptance, even more front and center when it comes to hydrogen VTOL. Lastly, Joby's far along in it's the leader in eVTOL progress. It's been flying since 2014. These two full-scale demonstrators in 2017 and 19 are aircraft I worked on as thermal team lead. In 2023, we started flying our production prototype, and we are well on track for full type certification with the FAA and with the Dubai Aviation Authority, as well as making progress in the UK CAA and EASA. We are very mature on this product, and the vast majority of the company is working on the eVTOL. A small part of it, which is my role, is the incubation and the development of the hydrogen system. The biggest part of it is leveraging as much as possible of the amazing, work that Joby's already done with eVTOL. Lastly, this is partly by Joby and partly with the answer. You may recognize this aircraft. This is from our subsidiary H2 Fly. It's actually a really cool aircraft because it has 2 fuselages. In this layout, you actually have the tank in the left fuse. That's why there's no window in the cockpit, but it can actually fly in a different configuration. It can fly as 4 passengers. And then on the right, there's a pilot. And that's because H2 Fly has flown this aircraft piloted with gaseous and with liquid hydrogen. And that middle pod, That's the powertrain. Inside here is the propulsion unit, the fuel cells. This aircraft, of course, is a development prototype. It's flown in Slovenia and Germany, but it was a huge, huge step for Joby to kickstart its effort on the fuel cell side. And so, this is the history of H2Fly and what matters for this conversation. It was actually a spin-off. So it's founded in 2015, but H2Fly already existed in the form of a DLR project with the same people that eventually founded the company well before 2015, and had already demonstrated gaseous hydrogen flights before Joby acquired it in 2021. Right around where I started working myself on hydrogen. Towards the end of 2023 in Slovenia, they actually worked with Air Liquide for a liquid hydrogen tank, the one I was mentioning on the left fuselage. And then in 2024, and key for the stuff that's about to come, we worked super tightly. I visited a bunch of times. They came over. We had people on site permanently. They developed the H2F-175, which is the LTPEM, the low temperature proton exchange membrane fuel cell that actually flew on Joby's hydrogen electric aircraft. Um, that's the star of today. So let's get into it. I finally got to this point this late in the presentation deliberately because of the value and the context that Joby, that hydrogen has, rather than just telling you about the story without anything around it or why it's so important. This is the aircraft as it's flying in Marina. It's actually this interesting moment where it's converting from vertical flight to forward flight. You can see the props are around 45. That's because it just finished with the props tilting upwards, and while it's in the air, it tilts forward and starts flying forward. The aircraft is, as you can imagine, a mix of what came before. So the battery electric is purely a battery pumping electricity into a motor, an electrical power unit. Whereas the hydrogen system, actually, the easiest way to explain it is it's recharging the battery in the background or just sharing the DC link, the terminal, the high voltage system. So in other words, your power can come either from the battery or from the fuel cell. And it can do that playing to the best of each of those strengths. Batteries have a quicker response time. Fuel cell have slower responses in terms of amps per second, how much they can change their amperage per second. But the net result is that the power unit requests a certain current and it comes. And so in that sense, it was actually extremely synergistic. Apologies for the business term. It's synergistic to throw the two things together, a fuel cell and a battery, and get it to feed the motor in the way it was used to. And then, of course, we went for a storage system. We actually went straight for liquid, about 40 kilos in a vacuum insulated door. 40 kilos is a number that made sense for this prototype. Of course, plenty of discussions in terms of what the valuable mass is for onboard hydrogen for a production version. But the key thing here is that it's liquid. The mass fraction of the tank and the volume of the tank with gaseous, just we believe, do not close or make a very hard case for hydrogen electric propulsion. So Joby went straight to liquid, jump-starting a team of hydrogen development for liquid storage. What else is valuable about the aircraft? So this is the aircraft as it's about to take off. As you see, the props are looking up. There's a few things that are worth mentioning. This is a prototype that had already flown as a battery electric aircraft for 25,000 miles. So it was tried and tested. The team knew what was happening. It was used to it. It was as much repeatable as possible in the sense that the operations, the safety, the procedure, all of that was well understood by the engineers designing it, by the flight test, the pilot. A lot of it was reused because that's the ultimate goal, is to piggyback on all the great effort the electric part of Joby's done to optimize the hydrogen system and make a range extender. So the aircraft that already flown, I mentioned there's a liquid hydrogen storage. Liquid hydrogen, for those of you who aren't super hydrogen nerds like most of us on the call, actually is stored at minus 250 C. That's around minus 450 Fahrenheit or 20 Kelvin. About 40 kilos on board. There's a lot of, as many of you know, there's a lot of technical requirements and complexities in storing liquid hydrogen at those temperatures. The system is actually designed to have a long lockup time, meaning, and this is a big challenge of the implementation, meaning the amount of time after which the hydrogen starts boiling and then venting off and you start losing hydrogen. Optimizing and increasing that time of lockup, the time you can let it sit, is a critical parameter because ultimately you want to get back to where normal fuel is, which is much like your car. You park it there and it stays for a while and you don't have to worry about boil off. On the left here, we actually swapped the battery weight. The battery doesn't need to be as heavy if it's not providing the range that it did for the electric product. So you can reduce the weight, provided you still have the power you need. and gain a bunch of mass that you can then use to insert the tank and the fuel cell. So you actually swap battery weight for hydrogen powertrain. One key thing is that even though the batteries were significantly heavier on the electric, these 25,000 miles the prototype flew as an electric aircraft were such that the aircraft never really exceeded 100 miles. I think it went a bit more than 100 miles in some conditions. 100 miles was the longest this aircraft flew throughout these 25,000 miles. And then within the first few flights of flying hydrogen, it hit 523 and then 560 miles. So, with a lot less work, it jumped straight to 5x an improvement in terms of range. As I mentioned, H2Fly was our close collaborator for the fuel cell. And then, as you may have guessed, the scoop under here is for external cooling. So batteries don't require that much cooling simply because they are 90% efficient, as we mentioned earlier. Fuel cells have a better efficiency than jet engines. They're at 50%. But does that mean that for every kilowatt you produce of power, of electrical power, you have about a kilowatt of heat that you have to get rid of? And so we designed and retrofit this carbon fiber scoop that inside contains a radiator, as you can expect, rejecting that heat using. One key thing I'll get to more in detail in a second is we had to build a permanent facility, temporary facility for aircraft storage and refueling. This is just the rendering, but the facility exists. I just didn't have an aerial view of the facility that looks as pretty as this one. This is actually what we submitted to the Marina, California Town Hall and Planning Commission. Really, what you're looking at is a chart trailer. I didn't put a photo because it looks like most liquid hydrogen trailers. And then the aircraft, both in its as stored position as well as in its refueling position, which is roughly what's shown here on the left. The facility it took a lot of work. I'll get to it in a second, but was designed to be lightweight, simple, but safe and FPA compliant, OSHA compliant. A lot of work happening there. The other thing that's worth noting is all this white versus the gray here. It's a lot easier if you're ever, decide to build a facility for yourself. It's a lot easier to just do everything on concrete. Concrete, unlike asphalt, can take liquid hydrogen spills, can take liquid air spills, and doesn't react with it. So the safe answer is always to work on concrete. And that was, what we needed. We needed to design the aircraft, retrofit as much as possible, reuse as much of the existing electric resources, get permitted and approved for this facility. And we were able to achieve, a 5+ hour flight. So this is a rendering, but the aircraft did fly in this actual pattern. This is Marina, California. It's just north of Monterey, somewhere in between. For those of you who don't know California, somewhere in the middle, north south middle of California. It's a beautiful place for Joby to be testing all of its aircraft, and specifically this aircraft. Would run circles of a few mile radius for hours and hours. It got boring after a while for the pilots and for the team to just watch this aircraft spin circles and do various flights at 500+ miles, the longest of which 161 miles for 5 hours plus. So takeaways, I'm gonna list stuff that will sound like, I don't want to say August, but that will sound to more of the more expert of you. It sounds stuff like you've heard before. The key thing here is I don't, I've seen a slide like this in the past, even before doing all this work. Now I believe it, having done the work, and I confirm it by putting only these 5 bullet points. I try to keep it as clean as possible. The first thing is, as I've repeated a billion times at this point, the fuel cells are the key enabler because they make the best part of hydrogen and electric. Not just because Joby's already got a great electric product, but because the physics of it are just significantly better, because the environmental item side of it is significantly more competitive. The fuel cell development for all applications, maritime, ground, storage, energy storage, and aviation, is progressing really quickly. Every week I speak to new suppliers that are coming out with tremendously valuable products. There's definitely an inflection point in my point in fuel cell supply, whether it's, H2Fly zone or external suppliers. There's a lot of development happening that will make fuel cell based aviation easier and easier. Number two, for aviation, that's not necessarily the answer for other modes of transport, but for aviation, liquid hydrogen is key. It does come with a penalty, especially the penalty of the boil off, the managing of it, design, penalty and safety if not well managed, and additionally a penalty in the cost of liquefaction. The mass fractions that are enabled by liquid hydrogen, there's no way on to the mass fraction, meaning the weight of the tank, the weight of the hydrogen divided by the weight of the tank. So if you have a 20-kilo tank of hydrogen, 20 kilos of hydrogen, and let's say 100 kilos of tank, that's 20%. That 20% is a good number. It's achievable with liquid, something you can exceed with liquid. Tanks out there are being built for 30, 40. With gaseous, I don't believe I've seen no clean answer to get higher than the 10% or so. So if you want to save mass, which is all that matters in aviation, you go straight for liquid hydrogen. The three hardest things that I thought a bit about this slide, it's not as pretty as the others, but I did think through this one the most. The hardest part of it were actually possibly not related to building the aircraft, but rather to do everything else around it. The infrastructure was hard. Developing, getting access to liquid hydrogen. We had to buy that chart trailer and ship it ourselves. I have to get a truck driver back and forth from the liquefaction facility. The regulation, so what exactly an FPA, EGA, all these various codes do for hydrogen and for a battery electric with a hydrogen tank right next to it, they're still being developed. So it's a tremendously hard part of the work is to understand exactly how to do it and making sure you're not breaking any regulation. And then third, not just Marina, California, who were super collaborative, the airport management and the city, but in general, there's a lot of authority having jurisdictions, meaning town halls, federal entities, all the entities that have a say in the government. They have a valid but an unease towards the novelty and the safety element of it and what it means for their fire marshals, what it means for their people, what it means for the community and such. Few minutes left. I do want to leave a bunch of time for questions. The first thing that is valuable is I actually went through a recent
Richard,
year old
well,
presentation
good. I was listening to Joby.
presentation by the DOE where they actually surveyed a bunch of experts and the actual the results are shown here and I think the top three, I think the top one is cost to end user. That's just a virtue of the remainder of the ones, but the need for sufficient infrastructure and public awareness actually ranked highest. And I now believe this statement and I believe the results of this survey on account of the things that myself and the team had to go through to make this happen. This is the hardest part. Need for technology advancements is hard, and that's why Joby is here, why companies are working on it. Top three, those will require a lot more than just what Joby can control. Very lastly, what happens next? What's the goal of all of this? So I mentioned New York, and I promise we're almost at the end. New York, as an example market, we build out as an electric company, electric aircraft company. We build out an infrastructure. That means you're flying from JFK to your party in the Hamptons, or perhaps to Jersey, or whatever it is in Connecticut. And from there, you've built a network of various vertiports where Joby takes off and lands. Some are helipads, some are recharging stations, and you have the multimodal service working. Joby expands its service from New York and starts building other localized networks. What does that mean? You can also do the same thing in Boston and within Boston and then in Washington. Now, where does hydrogen come in? You're at this point in time where Joby's already built a bunch of vertiports, a bunch of infrastructure, successful product on the electric. The Joby hydrogen system allows you to connect these. It aims to leverage as much as possible. And yes, this is the range. It aims to leverage as much as possible of the existing infrastructure. It aims to work in tandem with the electric, in tandem with commercial aircraft. But really what we're talking about here is connecting all of the East Coast and similarly connecting much larger areas, Paris to London and more of Southern England, most of California together. The range that hydrogen enables is such that this is possible. This is a map that I pulled from various data. It's capped to the range that I think it's 300 miles, 350. It's a huge amount of options. A lot of hub and spoke, a lot that are just corridors like the Northeast. The width of the band is the volume and the color is the actual price. Not that that's relevant, but you'd think that, 300, 400 miles is not that far for commercial aviation. There's actually a ton of flights today, and that's existing demand. That's not counting latent demand. The last slide I'll leave you with is Joby's mission is to save 1 billion people an hour a day. What does that mean with the electric product? That instead of sitting in traffic, you can take an electric aircraft to get to work and your commute goes from an hour to 20 minutes. What does that mean for hydrogen? It means that instead of taking your car or an Uber and then waiting through the airport, fastest people I know still do it in 30 minutes, and then flying, your commercial aircraft, and then, you land and you taxi and you deboard. Then you still are, in JFK or LAX, which are far from downtown. This is a 3 hour and 40-minute trip. Joby Hydrogen aircraft may be cruising slightly slower, such that instead of an hour and 20 to do the actual trip, it's an hour and 40. But you can take off from downtown LA. You can land in downtown SF or, downtown Manhattan or wherever it may be. So in that regard, you are saving a tremendous amount of time. And these are numbers that I've spent time corroborating, right? How long the average trip to an airport is, how long the average time through an airport is, even for business travelers. And then realistically on the other side, how much of a granular spread can we provide these heliports um, for an electric, for a hydrogen aircraft? And so this distance and difference in time on a trip like SFO to LAX, this is where the value is. This is where the customer can really benefit from this whole thing. This is why we're doing it. Thank you for listening through all of that. I'm aware I'm a bit over time. Let's open it up to questions, please.
Thank you so much, Raphael. That was incredible. We were at max capacity the entire time. Lots and lots of interest.
Awesome.
Yeah, I want to selfishly ask the first question. Well, maybe it's not a question, it's an invitation to explore the opportunities in Houston. I'm part of the Greater Houston Partnership and was at a luncheon the first week of December, and it was about 600 people, maybe more. I could not believe the words that I was hearing. I've never been in a city gathering that it was eVTOL, hydrogen, advanced air mobility, spaceports, airports, and the education among the community here in aerospace and aviation is ripe and we need it. There's a saying, Houston is an hour away from Houston. So we have our in-person annual conference called Flying High. This year it will be in Houston in December. So I want to just put that on your calendar for now. And I'm happy to facilitate some introductions and maybe explore some of those ideas. So don't forget December 24th. December 2025. Forgive me, I'm still getting used to it. Okay, first up is Doug. Doug, I see you have a few questions. If you could consolidate them into one, and we want to go quickly because there are lots of good questions. So, Doug, you can come on and ask your question. Doug Starfield.
Thank you. I was just wondering about the powertrain. If you had a Mirai type powertrain, since Toyota is a big investor in Joby, that's the question I just wanted to get answered.
Yeah, of course, Toyota is a big partner in this. They are mostly focused on our manufacturing and electric side. Um, I'm not too familiar with how the Mirai is set up, but the powertrain is, this is public information, is very basically liquid hydrogen tank that actually uses excess heat to heat up the liquid into gaseous hydrogen. So from minus 250 C to about 20 C, fuel cells can take a range of temperatures. From there, the actual power comes out at a certain voltage out of the fuel cell and is brought to the battery voltage with a DC to DC converter. And once you're there, you're actually sharing the bus with the 4 batteries that the aircraft already has. Joby's electric aircraft has 4 batteries. This hydrogen prototype has 4 lighter batteries, but there's still 4 redundant units. Those 4 live on the same voltage and bus as what the fuel cell is pushing. What's huge about this is they act as 5 independent units. To the point of redundancy I made at the beginning, anything in the aircraft can fail and the aircraft can still return safely to base. And this includes the fuel cell. It includes these lighter batteries. In other words, the batteries were sized for a safe failure of any component, including and especially the fuel cell. In other words, we actually were mostly concerned about the fuel cell misbehaving. And so we made sure that we had a reliable backup plan. And those were the batteries being on the same bus. Yeah, I don't know if that answers your question, but
Yeah, that's fine. Thank you. I know I shot a lot of questions at you, but you can, if you get time to email answers back, that'd be fine.
yeah.
I didn't mean to overload you.
Nice.
Thanks, Doug. Next up is Arnie Thompson. There was also a question about collaboration with Zero Avia. Is there collaboration not public or no?
So I will say this, there's huge opportunity for collaboration. They have come to us, and this is not shocking secrets, to congratulate us and to offer to work together. I've been to their facility and they've been to visit us, and the 2 CEOs know each other. We are trying to do the same thing. We're not fighting for a share of the pie. We're trying to make the pie bigger. I think what's actually been interesting is the focus of the collaboration and the focus of information exchange has focused mostly on the infrastructure and the safety elements. So, hey, how did you do this thing safely? A was a pressing question that we both had, and B was something we were much more, happy to answer for each other. Safety is generally something you don't want to hide for, IP reasons, but rather share so you're making someone else as safe as you can be. And then the other is the infrastructure. How did you get, the airport of Marina, the city of Marina, to be okay with liquid hydrogen inside the airport? Which parts are difficult of permitting? Which parts are going to take longest? So in that sense, the collaboration has been verbal and talking and meeting. But I think really highly of ZeroAvia. I've seen what they've done in the US, and I've been to the UK. They're solving an equivalent complementary part of this, right?
Yeah, it's one thing that I love about aviation, about hydrogen aviation and the eVTOL space is how collaborative everybody is and helps each other with certain things. It makes me really proud to be in this space. Suzanne, you're up next. If you're on, you can ask your question.
Thanks for a very nice presentation. I was just wondering of the storage of the hydrogen, because if you have it liquid, you either have to have very high pressure or you have to have it very cold. And you did mention that lower temperature, less wear on the material, but if it is too cold, it will get brittle. So how do you solve that?
No, absolutely. I mean, the liquid hydrogen element is probably one of the most delicates. I did err on saying, hey, we're not running combustion, so we're not hot. The cold part, there's a bunch of consequences. So first and foremost, hydrogen embrittlement is a concern. The effort there comes from selecting material selection. It sounds like an easy answer. It sounds like a straightforward answer, but it's an extremely difficult one. We were lucky to hire an expert from Ball who had done 45 years of NASA work, who had worked on Phantom Eye from Boeing. He was probably the most key person in making sure we were selecting the right stainless steel, the right aluminum grades. In other words, if you do your homework, hydrogen embrittlement and the very presence of cryogenic hydrogen onto metals, it can be solved, but it's very hard. It's one of those things where devil's in the detail. It's why it takes forever. You don't get it right at the beginning. You test coupons because it's not like everything's there. And that's for the hydrogen and the material compatibility. On the actual pressure and temperature, yes, hydrogen at 20 Kelvin is saturated at about 3 bar. Actually, the colder you go and the lower that pressure drops. Joby or not, the actual value here is to go as low as possible with pressure so that your tank requires lower and smaller and smaller pressure containment strategy, which is generally thickness and weight. So the name of the game here is to go from 6, 7 bar down to 2, 1.5, generally not going below ambient because you get massive safety hazards, but those are the values you want to be. One thing that I'm putting out here is the more development in liquid hydrogen pumps, the better off everyone will be because you can drop that tank pressure, make the whole thing lighter and more dense. But your fuel cell desires higher pressures, desires to go to 3, 4 bar, at least for LTPEMs. And so one's pushing down, one's pushing the other. And I see LH2 pumps as the answer to make the most there.
Thank you.
Thank you.
Fantastic question. Let's see. Next, we have Natessa. I hope I'm saying your name right.
Yeah, here you may not be able to answer this, but just curious if you can share the storage efficiency of the tank, the liquid hydrogen tank.
I don't think we can.
Okay, all right. Fair enough. I'd ask. Thanks.
Never hurts to ask. On Sandvig, you're next.
Yeah, excuse me. Couple questions. One having to do with the heat exchanger. As you pointed out, you got to reject about 50% of the energy in the hydrogen, which makes for a pretty big radiator. Doesn't that create a fair bit of drag? How does that affect the performance? That's the first question. The second question has to do with the speed you quoted, 200 miles per hour, I believe, is the normal cruise speed. And yet the max range flight appears to have been flown at, roughly half that speed. So I deduce that's best L over D is more like 100 miles an hour or so forth. Can you comment on that difference and what is realistic with respect to normal cruise speed operations?
For sure. There's actually a lot on the second question. I'm glad you asked it. So on the first one, the radiator adds drag. You can be very smart about it. We have a really good, interestingly, one of our chief scientist, head of aerodynamics, is the person who designed the H2Fly aircraft I showed you, Gregor. He's one of our longest execs, and he's a tremendous aerodynamicist. As an aerodynamicist myself, I used to go to him a lot. The radiator adds a bit of drag. It's manageable. It's in the single digits, roughly. It's a few things can or have been done. The first is depending on ambient temperature, much like other cars do, much like I worked myself on Teslas, you can put adjustable louvers. So depending on your ambient air and the heat demand, you can increase or decrease the airflow through the radiator. You keep the same flow rate, you keep high and hot radiators flowing a lot of coolant, but by decreasing the flow rate through the radiator, you can hit a certain mass heat transfer without losing drag. So that's one of the solutions. The other is with good aerodynamic design, you slow down the air and then reaccelerate it. That's been done with aviation, with cars. The one thing I will say that is a key important feature here is whether your fuel cell can run on the ground. I'm not saying that the Joby design that I showed does or doesn't, but one big decision that needs to be made when designing a VTOL aircraft is, does your fuel cell run on the ground? And if so, are you adding big heavy fans that enable static running of the fuel cell beyond very low power? So if you're running on the ground, you don't have any ram air running through that radiator. A good example that I've worked on myself is the fans in the Teslas in the Model 3. Those fans are actually designed for charging because you're actually rejecting a lot of heat and having to suck a lot of air through the radiator. Questions like that do come up. And so, yes, like John, you're adding a ton of drag if you're doing it, and you're adding some mass and some energy consumption if you're having to run on the ground. But generally, it's manageable to have that radiator in place if you design it properly and put it in the right place in your coolant loop. The second question was about speed. So the electric aircraft flies at 200. Our cruise speed wants to be 200. We were trying to set an endurance record, and both the maximum range and maximum endurance of that aircraft are roughly 100 miles, and therefore we flew much slower. Now, that said, if you're going to fly from, let's say, Washington, D.C. to Boston, we will not make you fly 5 hours or 3 hours at 100 miles an hour. A big part of the design, and this is agnostic, a big part of the design of this whole thing is what we call the toilet limit. You're not going to keep people in this. It's comfortable like a car would be, but you're not going to keep them more than an hour, maybe an hour and a half. And so what turns out is the faster you can go, the more operating range you call it. So not the actual distance the aircraft can fly at any speed, but what it can fly in an hour and a half or an hour. And that's a tremendous insight. It's basically saying, look, if you're going to up my power, this is how your market or whatever your operating range, this is the trips you can actually do before your customers have, an unpleasant experience. So for sakes of demonstrating a long endurance flight, 100 miles an hour is what we flew. For sake of a competitive product, we want to be more in the 200 miles an hour range, even if it means a loss in efficiency and more drag.
Perfect. Thank you.
Great question.
Sorry, I'm just talking away and muted. These are great questions. Next up is Antonio Tripoli, formerly Universal Hydrogen, and also was one of our instructors on our hydrogen aviation course with AIAA. Antonio, would you like to ask your question?
Yeah, thank you, Danielle, for the introduction, and thank you, Raffaele, for the very nice presentation. Just a simple question, and one is partly answered, very linked to the previous one. So hydrogen has very, very great features, but comes with some other features that are not great. For example, liquid hydrogen needs a tank, and so the tank takes volume. And my question is, this added volume takes some space from the volume that is allocated to the payload. So is the hydrogen version come with a penalty in terms of payload volume and ultimate payload with respect to the pure battery? And the second one is the fact that you need a radiator to cool down the fuel cell, brings some penalty in maximum speed with respect to the battery version. That were basically my two questions. Thank you.
Yeah, of course. I mean, the first one is a really valid insight. You come from Universal Hydrogen. I'm sure you've had, a lot of, you don't just believe these, but you've seen these yourself. What's interesting is having worked on both electric and hydrogen VTOL, this is the first time or you much more hit the volume constrained. So you're designing the aircraft, you have to get a number that ultimately closes. And way more often than I expected when I started, you're hitting both a roof, a ceiling, volume as you are in mass. And you're constantly asking your question, is this capped by volume? Is this capped by mass? For the prototype, the aircraft was unpiloted. And so we had much more space. We actually still had payload. The overall aircraft of the weight was still the same as the electric because of what I mentioned of saving batteries and gaining on the fuel cell. But that's the mass argument. The volume argument in the prototype, we took up a lot of the volume that would otherwise have been on payload. For a production version, a lot of things need to happen. So the first one is that I'm not going to hide this. A bunch of companies, a good example is GKN, have the strong thesis that you have to build the aircraft around the tank and you have to redesign existing solutions to make sure they work with this weird new volumetric requirement. Joby wants to piggyback as much as possible on the existing work, but is not opposed to, finding creative solutions, finding OML solutions that enable that system to fit, or at least, perform the mission that the product wants to perform without without shooting ourselves in the foot completely because of volumetric requirements. So that's kind of the overall. You either build the aircraft around the fact that you have a larger system by volume, or you create a way to increase that useful volume without affecting drag and other systems of the aircraft. The other thing that comes back to the question that Suzanne asked is how improved can you make um, your hydrogen density? And that means a bunch of things. That means don't waste it before you take off, increase your usable hydrogen, decrease your pressure, so you increase density. I think it's about 6% density increase every bar you go down, roughly. It's not linear. Another thing that I've been thrown around is cryocompressed. Today, cryocompressed has a massive penalty on mass, but a good benefit in density and in price, actually. I do think cryocompressed it's best for trucks because of that mass penalty being prohibitive for aviation but not for trucks. But absolutely, like the volumetric issue comes as frequently as the mass issue, which is less the case, is more frequently than what was for electric. On the radiator, 200 miles an hour is a manageable speed. You do have to be smart. You have to have good sizing requirements. You have to do your aerodynamics properly. But the drag reduction is not prohibitive, honestly. The drag increase is not prohibitive. The physical loads, if that's what you're asking, of a radiator at 200 miles an hour is acceptable. For faster aircraft, there's definitely questions about how you can go significantly faster without affecting the radiator. There's answers there too. Less answers I'm less familiar with, but there's ways to have radiators survive, Mach 0.5 or so.
Awesome. Great question. Next up is Martin Chan. Martin with Stratospheric Platforms. Interestingly enough, my first experience with hydrogen was in HAPS, High Altitude Platform System. So they're doing some cool stuff. But yeah, Martin, it's good to see you. Please ask your question.
Likewise. Thanks, Danielle. Thanks, Raphael, for the presentation. A simple question, if you're permitted to answer. What is the lockup time for your liquid hydrogen tanks? Could you comment about what that's driven by, something about your commercial operational assumptions, whether you want to leave the tank parked, fueled overnight?
Yeah, I don't know if I can give the exact number on lockup time. I will say, be cautious, depends how you define it. There's there's a fill pressure, and then there's the pressure at which you can run the system. It's really defined by um, depending on how you do it, but it's really defined by the delta between your venting pressure and honestly 1 bar. You can vent it down all the way to ambient, after which it just won't vent. And then the lockup time is defined mostly as that pressure range. So that gives you how many hours. In the single digit to day is generally a realistic number to go for. What's key here is also the heat leak for typical Sophie. Joby, did any of these? Sophie is a good answer, but it's terrible for reusability. For MLI, you are ultimately trading mass and how many MLI layers, multi-layer insulation layers you are doing. So it does become a question of how sporty. You can make a very sporty tank with a high mass fraction, but it's boiling off and you have to go, or you want to make a much more robust system. I've seen a bit of what Azarega Universal did. I think it was much more on this is a product, that doesn't, it's not an F1 car that if you don't go, stalls on you, but rather it's something that has a solid lockup time. We're sitting more on that. We're sitting with what Universal was doing. The lockup time should start from the beginning with something manageable. That said, I think what's key about aviation, and a lot of aviation, at least in the way I've presented it, the B2B element, or at least the element that it's managed by expert hands, whether you train them or not, it's a B2B product, makes it a lot easier for the safety for these lockup time issues than, a consumer car. And there's tons of reasons I could give, but one of them is the fact that all these things can be managed, written down into protocols, existing ConOps with iterations, with training. And so you can manage this problem better than you can with a lot of other applications for hydrogen.
Awesome. Thanks. We're about out of time. Do you have time for one more question?
I do, of course. Thank you
Okay,
all
this
for all
will
the
be.
questions.
You want to get through all of them? No,
There's so much to
I
answer, I
thought
think.
that's what you said. I wasn't trying to assume. I didn't hear you. What did you say?
Let's do it. Let's keep answering them as long as people are interested and can stay.
Okay, I think this is a good one. Do you release? This is Dennis. Dennis, I can't see your last name, but you can come on and ask if you're still here.
Hey, hi, Raffaele. Thank you very much for the great talk. I'm Dennis from Noveta. We design test facilities for cryogenic liquid rocket engines. So we deal a lot with cryogenic fluid. And I was wondering, what do you do with the boil off coming off the tank in the vehicle? Do you need to burn it, or you just release it into the atmosphere, or you use it in the fuel cells?
So you can do all three. The first two are generally the simplest. Interestingly, a boil off has actually worse. Sorry, a non-combusted boil off has um, a GWP 100 of 4 for every kilo
Mhm.
spent. It's 4 kilos of CO2, and the number goes down if you combust it. It's still not zero, but you combust it. When it comes to sustainability, I think boil off is probably the biggest issue. If we don't do this properly, we're wasting a bunch of hydrogen. This was a prototype effort. We did have boil off. We were using green hydrogen now, but that doesn't mean that the green hydrogen has zero emissions. It has some GWP. And so the first two are generally what I see happening for these types of efforts. It's harder to use the gaseous. It's not impossible, but I think the gaseous boil off um, is usable in a fuel cell. We've considered taking that boil off and just dumping into a fuel cell and generating power. At least you put it in the grid or you use it for running your utilities. The other valuable option that some companies are looking at, a good example being Gen H2, is small scale liquefaction. That doesn't mean super small, but if you have an airport and you have a system they all hook up to at night, you can commonize the liquefaction. You can also commonize, using a fuel cell for it. But the point being, you can actually salvage, and we will have to salvage the boil off from the system. I think the answer is probably 80% in being smart about your operations, and then 20, a good vent down done properly, and then the overnight storage, inerting, even ease of inerting, and then the 20% is all these wacky reliquefaction solutions running fuel cells.
Thanks.
Yeah, thanks. Great question. Okay, I think I see two more questions sorry, let me find my place in the chat. Okay, Jennifer, if you're on, I might ask if she doesn't unmute. What is the weight? And you might have already shared this. What is the weight percent of hydrogen for the LH2 tank?
I can't share the number, but I mean, companies are throwing 25 to 30 to 40% is the more sporty. So that's 25 kilos for a tank that is, full at 100 kilos, weighs 100 kilo full. Then number
Yep.
go up to close for a competitive product. It goes up automatically when you make a larger and larger tank. The larger the tank, the easier it is, but the harder part is that your stresses actually go up. So your tank size is limited by that internal stress of the actual aluminum or steel. But
Got it.
that 20 to 30, that's where things are with liquid right now.
Thank you. Richard, are you here? You can ask your question. Let me see if you're still here. I don't see Richard. Then there's Felipe. Are you here? I do see Felipe in here. Let me ask him to unmute. And this will be the last one. Thank you so much for doing this.
Thank you, guys. It's great to hear these questions. Find me on LinkedIn, add me. I'll try and answer it.
Yeah, so I don't
Help
see
everyone.
Felipe jumping on to ask his question. But I think you did address it some. I really want to respect your time. I think this is a massive gift that you have given to the hydrogen aviation community. It's, like I said, one for the record books. I see a lot of reporters and writers in here as well. So thank you so much, Raffaele. And definitely everybody here, come to Houston, December 2025. We're going to show you what's going on in Houston. So thank you so much to Joby. Thank you so much to everybody who attended, and a special thanks to you, Raffaele. Have a
Thank
wonderful
you
week.
so much to you, Danielle, for always being so awesome with this. I really think you're doing something huge here.
Thanks. Likewise. Bye, everyone.
Thanks, guys. Have a good MLK.
Happy MLK.